Okay, so thank you, Leo. So today it's a pleasure to have Philippe Sosoe. He's going to discuss fluctuations of stationary integral polymers in 1+1 dimensions, one for space and one for time. Okay. So.
Oh yeah, thanks everybody for coming. Thanks for the invitation. I'm going to be discussing, as was said, fluctuations of stationary integrable polymers in 1+1 dimensions. In fact, in this first lecture, I'll talk about a very specific mol, the semidiscrete mol that was introduced by O'Connell and Yor. And I will use this mol to illustrate a method to get some bounds on fluctuation exponents that was developed over the years, starting in work of Balázs, Kator, Seppäläinen, and then developed by Balázs and Seppäläinen further on several mols. And in the case of the O'Connell-Yor polymer, it was the general method was applied by Seppäläinen and Valko to that mol. We'll see a slightly different version, a slightly different interpretation of what they did, but it will serve as an introduction to the subject and what's coming in the upcoming lectures. So first, even though I'll focus on one specific mol, I will start, for people who've never seen this, to give some bit of background. I'll start by discussing directed polymers slightly more generally. So this mol was introduced by Hughes and Henley in 1985. They were studying what they called domain walls. So basically the easing mols with perturbations in their couplings, what they called impurities, and they were interested in random interfaces between plus and minus spins. And to model this, we can do the following. We can give ourselves a random walk. So a directed polymer mol will be a Gibbs measure on paths of length n. So you can think of starting with a random walk, simple random walk on Z, and then adding a field of IID random variables that have two indices. One is n, which we'll think of as time, and the other is a spatial index, which is not an integer. These potentials, V, are IID, so they're going to be random, and we're going to take them to have high moments in this case. There are many interesting questions when you have low moments, but in this case, we'll focus on the high moment case. And as I said, the polymer mol is a Gibbs mol. So there's a Gibbs weight that's going to be attached to each path. The weight that we attach to a path x1 up to xn, so here the xi, or a path of a random walk, so a path on Z, nearest neighbor path, is the exponential of beta times the sum from I equal 1 to n, so the sum along the length of the path, of V evaluated at I xi. This first index I here, the first index of V, ensures that we never see the same value of the same realization of a potential across different steps. So because we move across in time, that's makes sure that the xi, the path, never interacts twice with the same value of V, and that's what distinguishes this type of mol from non-directed polymer mols. So as usual, when we have Gibbs weights, we can build a partition function by summing over all the possible weights, by summing over the entire sample space. In this case, the sample space is paths of length n. So each path, since it's a random walk, each path has the same weight, but it's reweighted by this Gibbs factor, exponential of beta times the energy, sum from I equal 1 to n, of the V's evaluated at the different steps of the path. So we can visualize this as follows. You can think of a time direction here, a vertical direction in this picture, and a spatial direction being horizontal direction. At the first step, we can either go left or right. If we go left, we have the chance to interact with the potential V2 at this site. If we go right, we have a chance to interact with the potential V2 at the site to the right, and so on for further steps. In the second step, we can go up by 1 and we'll interact with the potential V3 and so on. So the first index of the potential represents time, and then there's a spatial index x. Very often, we flip this picture by 45 degrees, and instead of thinking of paths going up in time, so the vertical direction being time, we do this rotation and we think of paths that can only go to the right and up. So these are going to be directed paths, and each of these paths is weighted by a Gibbs weight that depends on which sites we visit along the way from the bottom here, 0 up to the top right corner. So the key quantity of interest here from the very beginning, including in Hughes and Henley's original work, and also for high dimensional work, the key quantity of interest is what's the location of the path as a whole. What is the location of the path when we measure it, not according to the random walk measure, but according to a reweighted measure where each path is given this random weight given by the Gibbs weight e to the beta times the sum of the values of the potential of the path, the values of the potential evaluated along the path of the given realization of the random walk. In other words, what's the expectation with respect to this quenched measure, this random measure here that gives weight to each path proportional to this exponential Gibbs factor? According to that measure, what is the location of xn? So in other words, if I look in this picture up here, the first picture, I know there's some delay in when I write things. How far am I from the origin? What's the typical distance from the origin? That is the key object of interest in the study of polymers. So what is expected in our specific case of sufficiently many moments and 1 + 1 dimension? So not higher dimension space. There's both 1 dimension in space and 1 dimension time. In that case, there's some fairly precise conjectures, and these conjectures actually partially go back to Hughes and Henley, who numerically studied this problem of the displacement from the origin after n steps. And these conjectures come down to the following. So I'm going to single out here a few quantities of interest. One of them is the log partition function. So remember, the partition function is the sum over all possible paths of the corresponding Gibbs weight. And remember that this is a random quantity. Because it's random, it depends on the random variables v, this random potential. So one conjecture is that this, in great generality here being for many different distributions of the weights v, the typical size, the typical fluctuations, the typical size of the difference, the distance between log z and the expectation should be n to the 1/3. Correspondingly, or relatedly, the typical displacement of the path, according to this random Gibbs measure, should be of size n to the 2/3. The typical displacement from, so this should be the displacement squared here. I'm sorry. The displacement squared should be, no, the displacement, I'm sorry. I'm getting confused. It should be of size n to the 2/3. There are also distributional results, so conjectures about what the distribution of the objects should be. In particular here, should be the distribution of log zn. Log zn should be of order n, but once we center it, once we remove an asymptotic quantity of order n, and we divide by the typical size of fluctuations, n to the 1/3, it's expected that we converge to the Tracy-Whittem GUE distribution. So that's the asymptotic distribution of the properly centered and rescaled maximum eigenvalue or minimum eigenvalue of a GUE random matrix. There are some known very precise results for exactly solvable models, and here the names that should be named among many are Sepulinen, Borden, Corwin, Ferrari, and also many other people, Imamura, Sasamoto, and so on. Actually, next lecture and in the next 2 lectures, especially in the next lecture, we will talk a little bit more about really for which discrete models that fall under this umbrella, that fall really in this setting that I introduced in the previous, not the previous slide, but on the pages above, for which models these different results are known. Instead, today, we're going to focus on a different model, a model that was a big inspiration in the study of these exactly solvable models. that's not a discrete model, it's a semi-discrete model. One of the directions, the time direction or the horizontal direction, if you wish, is going to be a continuous direction. And the reason for using that model, the O'Connell-Yor semi-discrete model, is that a lot of the computations are somewhat simpler, especially if we're trying to use this coupling method of Ballas-Kator-Seppäläinen. Okay, so what is the semi-discrete model of O'Connell-Yor? Let me give it some time to, I see it's a bit slower to update. So this model was introduced by O'Connell-Yor in a paper that's called Brownian Analogues of Burke's Theorem. A very important input to that paper was a paper by Matsumoto and Yor about certain exponential functionals of Brownian motion. And what is the model? It's very simple to describe if you know Brownian motion, which I'll assume here. So we give ourselves Brownian motions B1, B2 up to Bn, and these are going to be independent. I forgot to specify this. We have independent Brownian motions, and now we're going to construct a partition function, and we will think of this partition function as a polymer partition function. But before we get to this polymer interpretation, we can just look at this formula here. It makes sense, even if we don't talk about polymers. It's a multiple integral, actually an n-1 fold integral over the simplex S1 less than S2 less than Sn-1 less than T. And we're integrating the exponential of a sum of increments of Brownian motions across different values, across different SJs. So for the first Brownian motion B1, we look at Bs1 minus B1, 0. So B1 S1 minus B1, 0. B1, 0 is 0 because we're looking at standard Brownian motions. And for the second Brownian motion, we look at B2 S2 minus B2 S1, and so on. We always sum Bj Sj minus Bj Sj minus 1. Except that for the final Brownian motion, since we're only integrating over Sn minus 1, Sn, instead of Sn, will have T. Okay, so that's the partition function that we're going to be looking at. How is it related to what we were talking about just a second ago, these polymer models? Well, you can think of this n-1 fold integral as selecting an upright path that is semi-discrete. So it's a path that is constant, piecewise constant, and it increases from level 0 to level n, discrete level 0 to discrete level n. And the times of increase, so the time when we move from level 1 to 2, level 2 to 3, and so on, are the SJs. So you see a graphical representation here. We start at the first level. I think I said level 0. We start at the first level, level 1, and then at time S1, we jump to level 2. We spend time S2 minus S1 at that level, and then we jump at time S2 from S2 to S3, and so on. In this way, we go from the first level at time 0 to the nth level at time t. And on the jth level, we accumulate, say on the second level, for example, we accumulate a certain increment of a Brownian motion. To each of the n levels, we associate a Brownian motion, and we accumulate an increment corresponding to the length of time that our path spends on that level. Okay, so this is a semi-discrete, semi because it's still discrete in this vertical direction. There's still n levels. It's semi-discrete only because it is continuous in the horizontal direction. And so the interest in this model, the initial interest in this model is because it has a very useful, with respect to understanding the conjectures that I mentioned earlier. It has a very useful stationary version. First, I'll introduce it, and then I'll tell you why what is stationary about it. So to introduce it, we're going to make a slight modification, or rather an addition to the previous model. We're going to start by adding one more Brownian motion, B0. So that's why I said from level 0 to level 1. In the previous picture, there were only n levels. Now there's going to be n plus 1, and we're going to start at level 0. In addition to adding a Brownian motion, we're going to extend all the Brownian motions to be two-sided Brownian motions. All this means is that in addition to having the Brownian motion start at 0 and going from time 0 to infinity, we're going to extend it to negative times by adding independent Brownian motions to each of for each of the indices and then independent of each other as well. And these Brownian motions are run backwards. So they start at 0, and then at time s, if s is negative, they're given by the value of some Brownian motion at time minus s. Okay, so if you want the picture, you have a Brownian motion in this direction, and this is 0, and then you run another Brownian motion backwards in this direction. These are two-sided Brownian motions, but from now on, we'll just say Bj is a two-sided Brownian motion. That's what we mean. Note that if we do this, then Bj t minus Bjs, if t is bigger than s, that's still a Brownian increment. Okay, so add a Brownian motion, extend all the Brownian motions to be two-sided, and then choose a parameter theta that's positive. And now we modify the partition function that we had before in the following way. We have a partition function that's very similar to what we had before, where at each level we sum over increments of the Brownian motion, except that the 0 that we had before is replaced by an additional jump time s0. Also, the integrals now extend to minus infinity, and this parameter theta over here appears linearly in front of s0, the time of the first jump. Here's a picture associated to this. We have an initial level, which is now the level 0, and we have a first time. We have a time of a first jump. Okay, this picture is a bit messed up because we don't see the first jump, but the first jump is, say here, we jump at time s0 to level s1, and then to level 1, and then at time s1, we jump to level 2, and so on. Okay, the picture is still similar, except that now it extends all the way to minus infinity on the left. Okay, so what's the advantage of introducing this? Why did O'Connell and Yor introduce this partition function? The advantage is that it is stationary in the following way. So O'Connell and Yor say, first, just for notational convenience, introduce a 0th partition function that we're going. Oh, why does this integral converge? Yes, that's correct. It's not obvious. So first of all, here it's important that theta is positive, and then so start with you start with the s0 integral. It's important that theta is positive, so this theta times s0 factor actually is very small. Most of it is very negative most of the time, right? And then the Brownian motion grows like square root of s0, the Brownian motion for very negative times. Okay. Okay. So then, Okay, so for notational convenience, we're going to introduce a 0th level partition function, or rather its log, and this is going to be b0t minus theta t. Okay, and the reason for doing this is as follows. If we then write log of znt, so znt theta, remember, is this partition function, this multiple integral. If we write log of znt minus log of z0 theta t as a telescoping sum, this we could always do, we can always telescope. We write it as a sum of rj, where rj is log of zj minus log of zj minus 1. Okay. Then O'Connell and Yor's main result in their paper, their paper is not so much about polymers rather than this fact, this stochastic calculus fact, which is that for each t in R, the rj of t is the collection rj of t for j equal 1 to n is IID, so independent and identically distributed with a given distribution. It has the distribution log, it has the same distribution as log of 1 over x, where x is gamma distributed with parameter theta, with shape parameter theta. Okay. Actually, this is a consequence of O'Connell and Yor's result. They prove more than this, and in fact, quite a bit more. But we will only need, for today at least, and probably also for the remainder of these lectures, we'll only need this fact, this notion of stationarity. But O'Connell and Yor prove more, and more is true in many of these integrable models, these stationary integrable models. In fact, they don't prove only stationarity in time, they also prove a sort of stationarity in space. Okay, and this stationarity in space is as follows. We look at increments in time, but for fixed j of the partition function, centered by this theta t minus s, centered by this linear parameter t. What they show is that this is also a Brownian motion for each j. Okay, so this is a sort of stationarity in the levels instead of being a stationarity in time. In fact, they do even more than this. They prove something called the Burke property. They say that these increments both in the levels, so for example, here we have Rj. Rj is, remember, log of Zj minus log of Zj minus 1. And these time increments, so for example, here we have log of Zj minus 2 at S3 minus log of Zj minus 2 at S2. If you take a system of these time increments and space increments, or rather, these increments between levels, that's arranged along a downright path. So you choose times S1, S2 up to Sk, and then you construct the increments corresponding to these vertical. For each of the vertical segments that I draw here, you look at the corresponding Rj at the corresponding time, and you look at the corresponding increment in time. So for a fixed j, you look at the difference between log of z at that j at the two different times, adjusted by this linear factor. This collection is independent, okay, for each downright path. This is very useful when we study more geometric properties of the paths, but we're not going to use this here. Okay, I'm just pointing this out. When people talk about the Burke property, if this is the first time, or if you've heard about this before and you wonder how it's related to what we're talking about today, you know that it is this property that we're talking about. We're not going to use this in this lecture. We're only going to use the fact that if I look at the increments of the partition functions for different sizes, those are not only stationary in T, but in fact I know what their distribution is. Okay, so that will be absolutely crucial for us. The Burke property, the full Burke property, is quite a delicate fact. If you look at this paper of at least the original proof of, we'll call it Yor and Matsumoto Yor, which is a direct input to that paper, it's quite complicated. It uses something that Yor was developing at the time when he started talking to O'Connell, which is called the theory of enlargement of filtrations. He wasn't developing, he didn't invent it as far as I know, but he was studying it. Okay, but if you're only interested in the stationarity, if you don't care about the full Burke property, then there are proofs that are simpler just using stochastic calculus. For example, if you are interested in R1, if you just look at this, this toy model, this little integral here, this integral that looks like a one-dimensional integral that has this sort of flavor of the partition function that I showed you. So you take a Brownian motion, a two-sided Brownian motion, you integrate e to the b0t minus b0s minus t minus s theta from minus infinity to t. This is stationary in T, and you can compute its distribution. And you can do this just using standard stochastic calculus, no enlargement of filtrate. You can use Ito's formula and study this. Okay, this is sometimes called the Dufresne identity. This identity in distribution. Okay. Okay, maybe I should stop here and ask if there are any questions at this point. All right, so what have we done so far? We've introduced something that looks like a polymer partition function, and I told you it's a big result, but I'm claiming that it has a special stationarity property when we look at the differences of the logs for different sizes of the system. How is this related? How does that help us? So my claim for this lecture, the takeaway message is that thanks to this method of Balas, Kator, Sapelainen, this stationarity is sufficient to get, at least today we'll talk about the upper bound. It's sufficient to show that the fluctuations are at most of order n to the 2/3. And then in the coming lectures, we'll talk about what exactly that, how far can you go from there, also for other models. Okay, so let's talk about this. What are the consequences of this stationarity? So first, for notational convenience, I'm going to denote capital R, the sum of the RJs. Remember here, just so it's clear, RJ was log of Zj theta t. So I'm looking at the polymer partition function for size j, and I subtract the log of that. From that, from the log of that polymer partition function, I subtract the log of the polymer partition function of size j minus 1, and I'm in this stationary setting. Okay, remember that when j is equal to 0, we defined log of z0 theta t by b0 minus theta t. Okay, so the partition function that we're interested in, the one that conjecturally is of size n to the 2/3, has variance of size n to the 2/3, fluctuations of size n to the 1/3, can be written as a sum of these IID RJs minus b0t plus theta t. So now let's think about the case when both n and t are very large. Then the sum of IIDs, remember they have the distribution of log of 1 over a gamma function. That sum is going to be of size n. It doesn't have mean 0, so it's going to be of size n. And b0t minus theta t is also going to be of size t. Right? If t is very large, the Brownian motion is vanishingly small compared to theta times t. But what we're interested in is not this law of large numbers, which follows basically immediately from the classical law of large numbers, but rather the fluctuations. What's the size of log of z and t theta when we center it by its expectation? Okay, so note that what we've done is rewrite log of z and t as a sum of two terms, namely the Brownian motion up here, and the r, that's the sum of IDs. So we've written, after centering, we've written the quantity that we're interested in as essentially two sums of n and t IID random variables. Of course, the Brownian motion is continuous, but you can think of it as a sum of about t IID random variables. So we have two quantities of size square root of n and respectively square root of t, and we're hoping that their sum is of size n to the 1/3. Okay? So the only way this can happen is if there is some very effective cancellation between this b0t and the r, right? That's what we want to understand. And that's what this coupling method will allow us to do. So to see that cancellation as a first step, let's compute the variance. Let's try to compute the variance of log of z. Remember, the telescoping representation tells us that r, the sum of the rj's, is equal to log of z minus this b0 plus theta t, right? Now, sorry, this should be plus minus. Okay, so we can write the variance of r as the variance of these terms. This theta times t is constant, so we're just looking at the variance of a sum. So we get the sum of the variances plus the covariance. So what we're interested in is the variance of log z. So after rearranging, we find the variance of log z is the variance of r, the variance of the sum of IIDs. So it's n times the variance of any one of the r's, say r1. Okay, so minus t plus the covariance. b0 has mean 0, so the covariance is the same as the expectation of log z times b0. Now, I'm going to go over this pretty quickly, but the variance of R1 we can compute exactly because we know that the RJs have this distribution log of 1 over x, where x is a gamma random variable. So I'm going to leave this on the screen for just a moment, but once you know what the distribution is, this is just a calculus exercise. You can compute what you can at least write an integral representation or a representation in terms of the gamma function for what the common variance of the RJs are. And we're going to give that variance a name. We're going to call that psi1. And psi1 is the derivative of the logarithmic derivative of the gamma function. Okay, so this logarithmic derivative of the gamma function, I think is called, we're going to call psi, that gamma function psi0, and psi1 is its derivative. And its derivative is what appears is equal to the common variance of the RJs. So what this stationarity has brought us is that the variance of the partition function that we're interested in is equal to n times psi1 theta. Psi1 is this derivative of the digamma function minus t plus this cross term log z times b0. Remember I said the challenge for us is to understand the interaction, the cancellation between the two terms log of z and b0, right? Both of them are of size square root of t, respectively square root of n. And if we're going to get n to the 1/3 in the end, we need to find some cancellation between them. Well, the first sign of that cancellation between them we see in this first, of that possibility of cancellation, we see it reflected in that first term here. N times psi 1 theta minus t, it's a sum of two terms of opposite, it's a difference of two terms, of two positive terms. So we're going to be able to choose n and t so that this first term is small. So really what we're concerned with is the second term, this expectation of log z times b0. Okay, how do we understand this expectation of log z times b0? So remember here, what is log z? It's this partition function. It's a partition function for the stationary polymer. And the way we're going to massage that term or try to make progress is by using Gaussian integration by parts. So what is Gaussian integration by parts? You've probably seen it many times by now. So one possible statement is as follows. Suppose that f is smooth and also nice, say C infinity with compact support, and x and y are joint Gaussian. And we're interested in computing the expectation of some function of y times x. Then we can integrate by parts, and we find that this is equal to the covariance of x and y times the expectation of f prime of y. Okay, so that's the classical statement. Here we have, so here, meaning when we look at this term expectation log z times b0, we have a similar situation. But here we're being very symbolic. What do we really have here? We have b0 at time t, that's a random variable. And on the other hand, if we look at z, if we look at log of z, that depends not just on b0 of t, but it depends on the entire path, right? The entire path of b0 of s0 as a function of s0. There is a version of Gaussian integration by parts that will help us in this case, and it's easiest to present in terms of the Cameron-Martin theorem. So remember the Cameron-Martin theorem is the following. If you have a function such that it's square integrable, say on the interval 0 to t, we can compute exactly the Redon-Nikodym derivative of the distribution of a Brownian motion shifted by this function integral from 0 to t or 0 to tau of hs. The Redon-Nikodym derivative of that with respect to just a Brownian motion, and it is equal to this exponential factor here, e to the delta integral from 0 to t hs dbs. That's a Ito or Paley-Wiener integral, because we're integrating just a function that's deterministic, minus delta squared over 2 times the L2 norm, integral from 0 to t of h squared. If we differentiate both sides here, so let's not worry too much about what the derivative means, what sort of function f is, but assuming we're allowed to differentiate, if we differentiate both sides, that tells us that, reading from the right here, if we have the expectation of the integral, Ito integral of h dbs multiplying f, that's equal to the derivative of the expectation of f as a function of the path, but modified by a small delta times the integral from 0 to tau hs ds. We're going to apply this to study this term. So this term expectation of log z times b0. Because what we have is, we have the Brownian motion, b0t, and we have log of z, which depends on the Brownian motion. So if we apply it with the function h, if we apply this formula here, with the function h is indicator from 0 to t, then we find that the expectation of b0t log of z and t theta is equal to the derivative with respect to delta at delta is equal to 0 of this partition function modified by this term here. Okay. And now we have a very classical computation in statistical mechanics when we differentiate a linear term appearing in a Gibbs factor, appearing in a Gibbs measure, we just get the expectation of this linear factor with respect to the Gibbs measure. So symbolically, if you look at log of the integral of e to the delta x plus y, set delta equal to 0, differentiate and set delta equal to 0, you get the expectation with respect to this Gibbs measure e to the y of the quantity x. So here we're applying this to this partition function. So if we do go to the computation, the end result is we get the expectation with respect to a random measure, a quenched expectation. If you go all the way back to the very beginning, we had this quenched measure where we assign to each path, we assign the Gibbs weight given by the polymer partition function, the Gibbs weight corresponding to the polymer partition function. We divide by the polymer partition function. And here, what are we taking the expectation of? Well, we're taking the expectation of S0 times the indicator of 0 to t. So that's S0 plus. Okay, we only get S0 plus, the positive part of S0. Okay, so let's summarize everything we did. That's the steps we took, and let's write down finally this formula of Cepelin and Valco, this exact formula for the variance. So in summary, we said, O'Connell and Yor tell us that log of z and t minus log of z0 t, we can write as a sum of IID random variables, and that moreover we have stationarity in t. If we change the time, we're still IID with this given distribution. Then just by doing some arithmetic, we used that to write the variance of log z and t as the sum of two terms that, they can't really move, they're just constants, n psi 1 theta minus t, times the expectation of b0 times log z. And then we did Gaussian integration by parts, and we said we can transform this into the expectation of S0 plus. So y positive part of S0, because we're only modifying the Brownian motion for positive time. So the reason there was a question. Sorry, I'm going to answer this question. So over here, implicitly, what's implicit here is that time is positive. Okay, t is positive. The Brownian motion, the two-sided Brownian motion, B0t, B0 is formed from a Brownian motion for positive time and an independent Brownian motion for negative time. So when we apply Gaussian integration by parts, the Brownian motion for negative time is not affected. In other words, we only, when we apply the Cameron-Martin formula, we only modify the Brownian motion for positive times. Okay, so for positive S0, that's why you get S0 plus. There's no modification for negative S0. Does that make sense?
Thank you. Okay.
But yeah, this distinction between S0 and S0 plus will be important because if you just had S0 there, the result would be wrong, but also things would be much easier. So after, again, the three steps, O'Connell, yours say you can telescope and the increments are stationary. By arithmetic, you can rewrite it as this variant. You can rewrite the variance as the sum of three terms. The only interesting term is the last one. That last term finally gets us into real polymers. It gets us into the study of the quenched measure, the measure where we reweight by the paths. And if we put everything together, we get this really nice formula, which has analogs in all the models that I mentioned earlier, like starting with Ballas-Kator, Cepelin, and study of interacting particle systems. But the reason we selected this model, namely the O'Connell-Yor model, the reason we selected this model is that in that case, the formula is particularly nice. It's very simple. It's a formula that relates the variance to the constant plus S0 plus. So how far is the first jump? Remember what S0 plus was, right? S0 plus is the first jump. When do we jump from level 0 to level 1? How far is that? how much bigger is that than 0? Okay, and it will turn out that on average, it's at most n to the 2/3, something that's not obvious at all, but that's what it is, and that's what will give us the fact that the variance is also of order n to the 2/3. For people who know scaling relations, this is an exact scaling relation, if you wish. It relates the distance that the distance of the path to the straight line between, or this diagonal line, let's put it that way, and the variance of the partition function. Okay, so now our task, it still remains. I mean, it's nice that you can do all this, but now we have to evaluate expectation of S0 plus. And here we're going to deviate slightly from this traditional Balázs-Kantor-Seppäläinen approach. Everything that you see here, including this formula, even though it's presented differently, it appeared in this paper of Seppäläinen and Valko, and in fact, it appeared in many papers, previous papers of Seppäläinen and others, just in slightly different form. There's always this idea of relating S0 to log Z to a variance formula. And then the next step is, in most of these papers, is to try to sort of bind these two quantities together to another formula, and then, try to split the difference and show that both quantities have their expected size. We're going to do things slightly differently here. So we're going to use an argument that we came up with Christian Noah. So, okay, remember what the conjecture was? The conjecture is that this variance of log Z was equal to n to the 2/3. In this setting, in the stationary setting, this is not always the case. It's going to be true if we make a certain choice. If we choose these parameters n, theta, and t, so that this fixed deterministic term is of size n to the 2/3. Now you can ask, well, isn't it sort of cheating? What we'll see, in fact, is that once we know that the variance is of order n to the 2/3 when we make this choice of parameter, we'll be able to show that if either n or t is much bigger than the remaining parameter, so if n is, for example, much bigger, n times psi 1 is much bigger than t, or t is much bigger than n times psi 1, then in fact the behavior will be Gaussian. Okay, then remember we started by writing log z as a sum, log z bar as a sum of IID plus a Brownian motion, and we said, well, the Brownian motion is of order square root of t, and this is of order square root of n. And I'm telling you, if n and t are close to each other, then you can make this, you can exploit cancellation. It will turn out later on, once you know this, that it's very easy to show that if one of these two terms, if either n or t is such that it's much bigger than the remaining one, then that sum completely dominates and the fluctuations are back to Gaussian. Okay, so for this reason, we're going to just assume, we're going to place ourselves in this so-called characteristic direction, where n times psi 1 minus t is at most n to the 2/3. Okay, so our goal is to show that if we make that choice, then also the remaining term here, the remaining term being 2 times expectation of S0 plus, is also of order n to the 2/3. Okay, so how do we do this? The plan is as follows. We're going to start by replacing expectation of S0 plus. And here, see, I didn't write expectation with this ugly math BB. I wrote it just with an E. And by this, I mean the quenched expectation. This is still a random variable. It's the expectation with respect to this, this Gibbs measure on paths. We're going to compare expectation of S0 plus to just expectation of S0. The absolute value here is very important. And then the next is convexity. We're going to bring ourselves back to log of z and t, using the fact that this expectation of S0 is the derivative of log of z and t. Okay, so let's elaborate a little bit on these two steps. The first step, what is the comparison? What do we claim? My claim for the first step is that once we take expectations, S0 plus can be bounded by basically expectation of S0 plus an error that is smaller than the target bound that we're trying to get at. Remember, the target is n to the 2/3. That's the comparison. And then the second step, this convexity, well, what is that? If we look at the log of the partition function and we differentiate it in theta, then by the same computation that we discussed just a moment ago, this is going to be equal to the expectation, the quenched expectation of S0. Okay, so the quenched expectation of S0 is given by the derivative of the partition function. If we take a second derivative, then we get the variance. No, this is generally true. It's just the definition of equivalence. When you take a second derivative with respect to theta, we're going to get the variance of S0. And in this way, also very classical for statistical mechanics, since the second derivative is non-negative, the partition function is convex. If the partition function is convex, why is that interesting? Well, I just told you what we're trying to estimate, we can replace by expectation of S0. On the other hand, expectation of S0 is the derivative of the partition function, and the partition function is convex. Well, if you have a convex function, you can bound its derivative at a point by difference quotients, right? You can bound the derivative at a point by difference quotients. Here, I guess h is positive. So what that means for us is that expectation of S0, we can bound by difference quotients of the partition function. And that's nice because the partition function is what we actually can control. The partition function is the thing that we can write as a sum of IID increments, or almost as a sum of IID increments. Okay, so using these two ingredients, we're going to assume, the first ingredient, we're going to assume that we can make that replacement, replace expectation of S0 plus by expectation of S0, and I'm going to show you how you get the n to the 2/3 from this. And then, depending on how much time is left, I'll show you how to fill in the gaps and justify all the assumptions we'll have to make. So the first assumption is, let's assume, I'm giving it some time to update, let's assume that expectation of S0 plus can be replaced by just expectation of S0 at the cost of increasing the moments and taking a 1/2 power. Okay, then expectation of S0 plus, what are we going to do? Well, expectation of S0, I say we can replace this by difference. Maybe let me try to have everything on the same screen. Okay. Expectation of S0, we can replace by difference quotients, right? So we start by replacing expectation of S0 plus by expectation of S0, replace expectation of S0 by difference quotients, and then the next step is to center everything. So we have log of z nt theta plus h, log of z nt theta minus h, and then also the partition function at theta instead of theta plus h or minus h. So let's center everything. Let's add in here, let's add the expectations of the corresponding partition functions. If you do that, if you believe me, if you trust me, then the result of this operation, so replacing by S0, using convexity, inserting the expectation, so centering, and then taking what is it called? Just centering and then separate using the triangle inequality, not Jensen. The triangle inequality, we get the following result. We get that expectation of S0 plus is bounded by all these sums. Okay. Everybody okay with this? Okay, so now there are two final ingredients, and those will be the two final ingredients for the lecture. And they're very important because these are the ingredients that we want to generalize later when we want to look at different models and we want to see how far can we push this coupling method, possibly to models where we only know stationarity. We don't have this Burke property or fancier tools available to us. Okay, so let's use two final ingredients. The first ingredient will serve to get rid of these h's here. Here, we introduced this h parameter, which we still have not selected. We just said it's true for any h positive. We want to get rid of this h parameter and go back to the variance of log z, because that's what we're trying to estimate. The first ingredient of Cepelin and Valco is to say, okay, well, this difference is n times h. So if you change a parameter by h, you lose at most n times h when you take the difference of variances. The second ingredient, and that one is perhaps even more crucial, is that when we look at the difference of expectations, so if we look at these expectations that we had to insert to get variances here to center, the difference of expectations is quadratic in H. Okay, this quadratic behavior in H, this is, for people who know, this is curvature. Okay, that's how you see curvature in this setting. Okay, so if we assume this, then this whole set of equations of inequalities that I have at the top, it simplifies to just H minus 1 times the variance. We've removed the H's, all the H factors, so everything here is up to a constant factor. It's H minus 1 times the variance of log z theta to the 1/2 power, that's very important, times n to the 1/2 H to the minus 1/2. That's what we get from the from adjusting the variance, times n times H. That's what we get from adjusting the expectation after dividing by H here. Okay, so as I said here, H was still a free parameter. This was true for every positive H. Let's choose H so as to make these two error terms of the same order. Okay, if you choose H to make these two error terms of the same order, that fixes H. That's where the 1/3 finally appears. Okay, so you choose H to be n to the minus 1/3 if you want these two error terms. The error term coming from curvature, changing how does the expectation, the first order behavior, react to changing the parameter, changing the parameter theta, and how does the variance change when we change the parameter. If we set these two equal to each other, as they appear in the expectation in the equations, that's where we get the n to the minus 1/3. Okay, so it was really crucial that we have power 2 here. Okay, and so all of these computations, remember, why were we interested in this guy? We're interested in this guy because the variance of log z was expressed as some constant plus the expectation of S0 plus. Okay, so we've succeeded in bounded this expectation of S0 plus in terms of the variance, but to a power 1/2. So if we plug everything back in, we find that the variance of log z is bounded by n to the 2/3. That's what you get when you set H to be n to the minus 1/3 times n to the 1/3 times the variance to the 1/2. So if you call this variance v, you have that v, which is non-negative, is bounded by n to the 2/3 plus n to the 1/3 v times n to the 1/2. And so here you see that v cannot be bigger than n to the 2/3. Otherwise, this inequality is violated. Okay, so that's how you get the upper bound, n to the 2/3. Okay. So again, what were the steps? It was stationarity from O'Connell-Yor. Then by arithmetic and integration by parts, we obtained this Cepelin and Valco formula relating the variance to the quenched expectation of S0 plus, the time of the first jump. And then this time of the first jump, we relate to the expectation of S0. And this expectation of S0, by convexity, we relate it back to the partition function. Okay, and then we get a closed equation that tells us that v has to be at most of order n to the 2/3. Okay, are there any questions about this? So this argument is very simple once it's distilled like this, and it will be crucial later because it turns out that it's a very robust argument. It's a robust argument that can be extended to situations where we know stationarity, but where we're not even really in this setting of a polymer. Okay, so I don't have too much time left. I can very quickly, let's see. I can very quickly just tell you what did I leave out. I don't think it makes sense for me to start any computations here. But what did I leave out so that you know what was left? What did we assume? We assume this comparison of expectation of S0 plus to expectation of S0. That's one thing. And we assume these two estimates. Okay, so we assume that when we shift the expectation, we shift the parameter, sorry, by h, we shift the expectation by h squared. And we assume that when we shift the parameter, we shift the variance by h. Okay, so I guess of these estimates, the only one that I'm going to show you now, because it's very easy and it's also sort of interesting to see where the h squared comes from. The easiest is the difference of expectations. That's because the expectation is an exact computation. We can compute it exactly because we know that log of znt theta plus h is a sum of IIDs. these IIDs are log of, have the distribution of log of over a gamma random variable with parameter theta plus h plus a bounded motion. So it's an exact computation here. Let me remind you here that theta, that size 0 of theta was this digamma function, okay, the logarithmic derivative of the gamma function. Okay, so if we look at the difference of two of these expectations, where theta is replaced by theta plus h, we see that we can Taylor expand this psi 0 theta minus psi 0 theta plus h, and that brings in this function psi 1, this derivative. I think it's a trigamma function, the derivative of the logarithmic derivative. And the error is of order h squared. And now what remains is to note that this h, if we factor it here out h here, we have h times t minus n psi 1 of theta. Okay, but that's exactly the term that we assumed is of order n to the 2/3. So we get this error, actually lied earlier on, we get this error h times n to the 2/3. So we're going to get this extra error term n to the 2/3, but that works out perfectly with what I showed you above. So out of the three things that I asked you to believe, this difference of expectations is the easiest. Perhaps tomorrow I will show how the first and third works, and then we will see how to adapt this to other models, and also how to ask finer questions. For example, what happens to S0, to the distribution of S0 further out in the tail, not just the expectation. That's something that we investigated with NOAC last year. And there's also a little twist if you try to adapt this to other models, because you no longer have integration by parts. You don't longer have Gaussian integration by parts. And okay, so maybe let's leave it at this for today. And thanks for listening, and happy to answer any questions.
Thank you, Philippe. Let me invite everyone to unmute themselves.